What if I told you that the force keeping you glued to your chair right now, the force we call gravity, might not actually exist? What if everything you've been taught about gravity since childhood is fundamentally wrong? Not incomplete, not simplified, but wrong at the most basic level. Here's what will blow your mind. According to our best understanding of physics, gravity isn't a force at all. It's not made of anything. It's not pulling you down. And the greatest minds in physics have spent a century arguing about what it actually is, and they still don't agree. Think about that for a second. We've mapped the human genome. We've landed robots on Mars. We've photographed black holes. But the thing that keeps your coffee in your cup, we're still fighting about what it fundamentally is. In 2017, scientists detected gravitational waves for the first time, ripples in the very fabric of space itself, and won the Nobel Prize. But here's the kicker. Those waves might be made of particles called gravitons that we've never detected and might be impossible to detect. Ever. We're talking about phantom particles that might constitute one of the four fundamental forces of nature. But we can't see them, can't measure them directly, and might never be able to prove they exist. And that's just the beginning of how strange this gets. Before we dive into the deepest rabbit hole in physics, smash that like button, because you're about to question everything you think you know about reality. Hit subscribe. This video is going to rewire your brain. And drop a comment telling me what country you're watching from and what time it is where you are. I want to know where in the world people are ready to have their minds blown right now. Are you watching this at 3 a.m. because you can't sleep? At lunch break? Let me know. Let's start with what you think you know. You drop an apple, it falls. Isaac Newton sits under a tree in 1666, gets bonked on the head. Actually, that probably never happened, but it's a great story and discovers gravity. He writes down some equations, and boom, we understand gravity. Right? Wrong. And Newton knew it. Here's what Newton actually discovered. He figured out how to calculate gravity. He gave us the mathematical rules that let us predict exactly how objects with mass attract each other. His equation is beautifully simple. The force between two objects equals the gravitational constant times their masses divided by the square of the distance between them. With this one equation, we could predict the orbits of planets, the trajectory of cannonballs, the motion of the moon. But Newton himself admitted he had no idea what gravity actually was. In his own words, written in 1692, that gravity should be innate, inherent and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Read that again. The man who discovered gravity thought the idea that gravity could work the way his equations said it worked was absurd. He called it an absurdity that no thinking person should believe. So what was Newton's problem? The action at a distance problem. Think of it like this. You're standing on Earth. The sun is 93 million miles away. According to Newton's equations, the sun is pulling on you right now. But how? How does the sun reach across 93 million miles of empty space and grab you? What is doing the pulling? What is stretching across that void to exert force on you? Newton had no answer. He gave us the how much, but not the how or the what. For over 200 years, physicists used Newton's equations and tried not to think too hard about this philosophical nightmare. The equations worked perfectly. They got us to the moon. They predicted the existence of Neptune before anyone saw it, just from the wobbles in Uranus's orbit. Why worry about the deeper meaning when the math works? But here's the twist that changes everything. Newton was right to be bothered. Because when Einstein came along in 1915 with general relativity, he revealed that Newton's entire framework was wrong. Not approximately correct, not close enough, but fundamentally misunderstanding reality. Einstein said, "There is no pulling." There is no force reaching across space. Gravity isn't made of anything, because gravity isn't a thing at all. What if I told you that when you're sitting in your chair, you're not being pulled down? You're trying to move in a straight line through curved space, and the ground is pushing up on you, accelerating you upward, preventing you from following your natural path? That sounds insane. It sounds backwards. But it's the heart of Einstein's revolution, and understanding it is going to crack open your perception of reality. Here's what will blow your mind. According to Einstein, when you're standing still on Earth, you are being accelerated. Right now, constantly. The ground beneath your feet is pushing you upward at 9.8 meters per second squared. You're not stationary, you're accelerating upward. Wait, you're thinking, that's ridiculous. I'm standing still. I'm not moving, let alone accelerating. But Einstein would say you're confusing coordinate motion with proper motion. In the curved spacetime around Earth, standing still on the surface means you're constantly being accelerated away from your natural path through spacetime. Think of it like this. Imagine you're in an elevator in deep space, far from any planets or stars. The elevator suddenly starts accelerating upward at 9.8 meters per second squared, exactly Earth's gravity. You'd feel pressed to the floor. If you dropped a ball, it would appear to fall. If you jumped, you'd come back down. Everything would feel exactly like gravity. Now, Einstein asks, what if you're in an elevator on Earth, standing still? And I tell you that there's no way for you to tell the difference between being in that accelerating elevator in space versus standing on Earth. No experiment you could do inside that elevator could distinguish between the two scenarios. This is the equivalence principle, and it's one of the most profound insights in physics. Einstein realized it in 1907, and later called it the happiest thought of my life. The effects of gravity and the effects of acceleration are identical. Completely, utterly, fundamentally identical. But here's where it gets wild. If standing on Earth is equivalent to being in an accelerating elevator, then the force you feel isn't gravity pulling you down. It's the ground accelerating you upward. The ground is pushing up on you, preventing you from following your natural trajectory through space-time. But what natural trajectory? You ask. I'm standing still. No, you're not. You're moving through time. Every second, you're advancing 1 second into the future. That's motion through space-time. And in the curved space-time around Earth, if nothing interfered with you, your path through time would gradually curve until you are also moving through space toward the center of Earth. The ground interrupts that natural path. It pushes up on you, forcing you off your natural trajectory, causing you to feel weight. When you're in free fall, when you jump off a diving board or ride a roller coaster over a hill, you feel weightless. That's not because gravity stopped. It's because nothing is pushing on you. You're finally following your natural path through curved spacetime. You're not being accelerated. For those brief moments, you're moving freely, and it feels like floating. The International Space Station astronauts aren't floating because there's no gravity up there. Earth's gravity at the ISS altitude is still about 90% as strong as on the surface. They're floating because they're in continuous freefall, following their natural curved path through space-time around Earth. The station and everything in it is following the same curved path, so relative to each other, nothing accelerates. Hence, weightlessness. Here's the revelation that should be sinking in. Gravity doesn't pull, space curves. And objects follow the straightest possible paths through curved space. Those paths look curved to us, so we invented the concept of a force to explain it. But there's no force. There's no pulling. There's just geometry. John Archibald Wheeler, one of the great physics educators of the 20th century, summarized general relativity in one sentence. Space-time tells matter how to move. Matter tells space-time how to curve. That's it. That's gravity. Mass and energy curve space-time. Objects follow the curves. What we call gravity is the sensation of being prevented from following those curves. But this immediately raises a question that's going to launch us deeper into the mystery. If gravity is just curved spacetime, just geometry, then what are gravitational waves made of? When two black holes collide and send ripples through spacetime itself, what is rippling? If there's no substance, what's waving? Keep that question in your mind. We're coming back to it, because the answer is going to force us to confront whether Einstein's beautiful geometric picture is actually complete. Let's dig deeper into what curved spacetime actually means, because this is where most explanations fall apart. You've probably seen the rubber sheet analogy. Space is like a stretched rubber sheet. A massive object creates a dip in the sheet, and smaller objects roll toward the dip, right? Here's the problem. That analogy uses gravity to explain gravity. The ball rolls down the dip because gravity pulls it down. But we're trying to explain gravity in the first place. It's circular reasoning disguised as explanation. So let's do this properly. What is spacetime, really? Spacetime is the four-dimensional stage on which reality plays out. 3 dimensions of space, 1 of time. In our everyday experience, space and time seem separate. Space is where things are. Time is when things happen. But Einstein's special relativity showed they're woven together. How much of your motion is through space versus through time depends on your reference frame. Think of it like this. Imagine you're walking north at 3 miles per hour, and your friend is walking east at 3 miles per hour. You're both moving at 3 miles per hour, but through different dimensions of space. Your northward motion is her stationary direction. Her eastward motion is your stationary direction. You're moving through the same space, just rotated relative to each other. Special relativity says time is another direction like that. You're always moving through space-time at the speed of light. Yes, you right now, but that motion is divided between space and time. If you're sitting still in space, all your motion is through time. If you could move through space at the speed of light, all your motion would be through space, and you'd experience no passage of time. Photons do this. They don't age. Now, general relativity adds that 4-dimensional spacetime can curve. And here's the crucial insight that everyone misses. It's primarily curving in the time direction. When you're standing on Earth, the curvature of spacetime is mostly a curvature of time, not space. Time passes more slowly closer to Earth than farther away. This was proven in 1976 by Robert Pound and Glenn Rebka at Harvard, who measured that a clock on the ground floor of a building ticks slower than a clock on the top floor. The difference is tiny, a few nanoseconds per day, but it's real and measurable. This curvature of time is what causes the phenomenon we call gravity. Here's how. Imagine you're at the top of your trajectory through spacetime, in freefall. At that instant, you're not moving through space. You're momentarily stationary at the peak. All your motion is through time, but time is curved. Time is flowing slower near the ground than where you are. So your path through time naturally curves toward where time is flowing slower downward. A moment later, you're moving down through space. The curvature of time has become motion through space. That's it. That's the mechanism. The curvature of time creates what we perceive as gravitational acceleration. Think of it like water flowing downhill. Water doesn't flow downhill because height pulls it. It flows downhill because that's the lowest energy state, the natural path. Similarly, objects don't move toward massive bodies because of a force. They follow the natural path through curved spacetime. But here's where it gets truly mind-bending. The curvature itself is created by energy and mass. Einstein's field equations, published in November 1915, are 10-coupled, non-linear, partial differential equations that describe exactly how the distribution of energy and momentum determines the curvature of spacetime. They're some of the most beautiful and complex equations in physics. On one side of the equation, you have the geometry of spacetime, its curvature. On the other side, you have the stress energy tensor, a mathematical object that describes the density and flow of energy and momentum. The equation says, the geometry here equals the energy momentum there. Curvature equals stuff. The presence of stuff warps the shape of spacetime. What if I told you that the curvature creates real physical effects? In 1919, Arthur Eddington led an expedition to observe a solar eclipse and measured the bending of starlight passing near the sun. Einstein's equations predicted the sun's mass would curve spacetime enough to bend light from distant stars by 1.75 arcseconds. Newton's theory predicted half that. Eddington's measurements confirmed Einstein's prediction, and Einstein became a global celebrity overnight. But here's the revelation. Light has no mass. Photons are massless. So why do they follow the curvature? Because they're following the straightest possible path through curved spacetime. Light always travels in straight lines. Geodesics, the four-dimensional equivalent of straight lines. When spacetime is curved, those geodesics are curved. This is how gravitational lensing works. The Hubble Space Telescope has captured stunning images of galaxies bent and distorted by the curved spacetime around massive galaxy clusters between us and them. Some galaxies appear multiple times in the same image, their light bent along different curved paths to reach us. Einstein predicted this in 1936, but thought it would never be observed because the alignment required would be too rare. He was wrong. We've now cataloged thousands of gravitational lenses. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole technically, the shadow of the black hole M, 87 asterisk against its surrounding accretion disk. That image shows spacetime curvature so extreme that light orbits the black hole multiple times before escaping. The photon sphere. This is spacetime curvature made visible. So Einstein's geometric picture works. It's been tested thousands of times. GPS satellites must account for general relativistic time dilation, or they'd accumulate errors of several kilometers per day. We've measured frame dragging, the way rotating masses twist spacetime around them, using satellites and gyroscopes. We've seen stars orbit the supermassive black hole at our galaxy's center, following perfectly the paths predicted by curved spacetime. But here's the cliffhanger that's going to haunt us. If gravity is just geometry, if it's just the shape of spacetime, then why does quantum mechanics demand that every force be carried by particles? Electromagnetism is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. So where are the gravitons? What is gravity made of at the quantum level? And that question is about to tear physics apart. We need to talk about the elephant in the room, the crisis at the heart of modern physics, the problem that's consumed brilliant minds for nearly a century. General relativity and quantum mechanics are incompatible. They're both right. They're both tested. They're both incredibly accurate within their domains. And they fundamentally contradict each other. General relativity describes gravity as smooth, continuous, curved spacetime. It works perfectly at large scales: planets, stars, galaxies, the entire universe. Quantum mechanics describes reality as choppy, discrete, probabilistic. It works perfectly at small scales: atoms, particles, forces. And they cannot both be true at the fundamental level. Here's why. Quantum mechanics says that at the smallest scales, the Planck scale, about 10 to 35 meters spacetime itself should be a seething foam of quantum fluctuations. Virtual particles popping in and out of existence. Spacetime itself should be grainy, discrete, fundamentally uncertain. You can't zoom in infinitely on spacetime any more than you can zoom in infinitely on a photograph and keep getting more detail. At some point, you hit pixels. But general relativity treats spacetime as a smooth continuum, infinitely divisible. You can do calculus on it, take derivatives, assume it's smooth at all scales. If spacetime is fundamentally discrete, the entire mathematical foundation of general relativity collapses. This isn't just a philosophical problem. It's a real crisis that shows up when we try to understand extreme situations. What happens inside a black hole, where quantum effects and extreme gravity both matter? What happened at the Big Bang, when the entire universe was smaller than an atom? We can't answer these questions because our theories break down. Enter the graviton, the hypothetical particle that supposedly carries the gravitational force. If gravity is really a force like electromagnetism, then by the logic of quantum field theory, it must be mediated by particles' gravitons. These would be massless particles, traveling at the speed of light, carrying spin-2 angular momentum. Physicists can write down the equations for gravitons. The theory looks mathematically consistent, at least at first. When you try to calculate how likely two particles are to interact via graviton exchange, you get sensible answers for low-energy interactions. Great, but then you try to calculate what happens at high energies, and the theory explodes. Literally, the math gives you infinite answers, infinities everywhere. The theory is non-renormalizable, which is physics speak, for the math breaks and we don't know how to fix it. This is where quantum field theory has a problem with gravity that it doesn't have with other forces. With electromagnetism, when infinities appeared in calculations, physicists developed a technique called renormalization, essentially a mathematically rigorous way to subtract infinities to get finite physical answers. This sounds sketchy, but it works, and it's given us some of the most accurate predictions in science. The magnetic moment of the electron, calculated via quantum electrodynamics, matches experiment to 11 decimal places. But renormalization doesn't work for gravity. The infinities in quantum gravity are too nasty, too pervasive. No matter what tricks physicists try, they can't get consistent, finite answers for high-energy gravitational interactions. What if I told you that this might mean gravitons don't exist at all? That treating gravity as a quantum field theory might be the wrong approach entirely. Some physicists think gravity might be an emergent phenomenon, something that arises from more fundamental quantum degrees of freedom, the way temperature emerges from molecular motion. Eric Verlinde at the University of Amsterdam has proposed that gravity is an entropic force, arising from information theory rather than fundamental interaction. In this view, asking what gravity is made of is like asking what temperature is made of. Temperature isn't made of anything. It's a statistical property of many particles. Maybe gravity is similar, but here's the challenge. We have good reasons to think gravitons should exist. In 2015, the LEGO collaboration detected gravitational waves from merging black holes, proving that gravity can propagate as waves through spacetime. Waves are quantized in quantum mechanics. Electromagnetic waves come in discrete packets called photons. So gravitational waves should come in discrete packets called gravitons. The problem is that gravitons would be absurdly hard to detect, like potentially impossible, even in principle hard. Freeman Dyson calculated in 2013 that detecting a single graviton would require a detector so massive that it would collapse into a black hole. You'd need to collect the energy from an entire supernova and focus it into a detector the size of Jupiter just to have a chance of detecting one graviton. And the act of detecting it would create so much gravitational disturbance that you couldn't tell what you'd detected. So we have a particle that theory says should exist, that we have good reasons to believe exists, but that we can never detect. How do you do science with that? This is the paradox of quantum gravity. We need to quantize gravity to make it consistent with the rest of physics. But when we try, the theory breaks. And even if we fix the theory, we might never be able to test it experimentally. Let me tell you about the Planck scale to show you how deep this problem goes. Max Planck, in 1899, realized you could combine three fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics, to get natural units of length, time, and energy. The Planck length is about y minus 35 meters. The Planck time is about y minus 43 seconds. The Planck energy is about yp billion electron volts. The Planck scale is where quantum effects and gravitational effects become equally important. It's the scale where space-time itself should be wildly quantum, where our current theories definitely break down. And here's the crushing reality. The Planck energy is about a quadrillion times higher than anything we can produce in particle accelerators. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies around 1013 electron volts. To probe Planck scale physics directly, we'd need an accelerator the size of the galaxy. We might be permanently locked out from experimentally testing the fundamental nature of quantum gravity. The universe itself might prevent us from building experiments that can probe the scale where gravity becomes quantum. So where does that leave us? With a bunch of competing theories, all of which make predictions we can't test, at least not directly. String theory says space-time is made of tiny vibrating strings in 10 or 11 dimensions. Loop quantum gravity says space-time is made of discrete loops forming a spin network. Causal set theory says space-time is fundamentally a discrete, partially ordered set. Each approach tries to solve the quantum gravity problem. None has been proven. None has been ruled out. And this brings us to a deeper question. What does it even mean to ask what gravity is made of? Are we asking the right question? Let's dive into the most famous attempt to answer what gravity is made of, string theory. And I need to warn you, this is where physics starts sounding more like science fiction than science. But it's real theoretical work done by thousands of serious physicists over decades. String theory says that the fundamental constituents of reality aren't particles. They're tiny, vibrating strings. These strings are unimaginably small, operating at the Planck scale. Different vibration patterns of strings correspond to different particles. An electron is a string vibrating one way. A quark is a string vibrating another way. And here's the kicker. One of the vibrational modes of strings is the graviton. Think of it like this. A guitar string can vibrate in different modes, first harmonic, second harmonic, and so on, producing different notes. Similarly, fundamental strings can vibrate in different modes, and each mode corresponds to a different particle with different properties. The graviton is just one note in the cosmic symphony. In string theory, the graviton isn't optional. It emerges automatically from the mathematics. When physicists first developed string theory in the 1960s and 1970s, initially to understand the strong nuclear force, they kept finding this massless, spin-2 particle appearing in their equations. At first, they thought it was a problem. Then they realized, holy crap, that's the graviton. We found gravity inside a quantum theory. This was huge. String theory naturally unified gravity with quantum mechanics. The infinities that plagued other approaches to quantum gravity were tamed by the extended nature of strings. When you calculate particle interactions in string theory, instead of point particles colliding at a single point, which creates mathematical infinities, you have smooth string interactions. Strings merge and split smoothly, and the calculations give finite answers. Brian Greene, one of string theory's most eloquent advocates, has described it as potentially the theory of everything, a single framework that explains all forces and all particles. If string theory is correct, then asking what gravity is made of has a clear answer. Gravity is made of gravitons, which are vibrations of fundamental strings. But here's where it gets weird. For string theory to work mathematically, it requires extra dimensions. Not the 4 dimensions we experience, 3 of space, 1 of time, but 10 or 11 total dimensions. The other 6 or 7 dimensions must be curled up so small that we can't perceive them, compactified at the Planck scale. Think of it like this. Imagine a garden hose seen from far away. It looks one-dimensional, like a line. But an ant crawling on it would discover a second dimension a circular dimension wrapping around the hose. String theory says our universe is like that hose. We see 4 large dimensions, but there are additional dimensions curled up so small that even our finest instruments can't detect them. The way these extra dimensions curl up their geometry, their topology, determines the physics we observe in our 4-dimensional world. Different geometries give different particle spectra, different force strengths. There are potentially 10,500 different ways to compactify the extra dimensions, each giving a different possible universe with different laws of physics. This is called the landscape of string theory. And this is where string theory starts to trouble even its supporters. If the theory predicts 10,500 possible universes, how do we figure out which one we're in? How do we test it? Every possible observation might be consistent with some corner of the landscape. The theory becomes almost unfalsifiable. What if I told you that string theory has made essentially 0 testable predictions in nearly 50 years? It's made a lot of postdictions explaining things we already know, but very few predictions that could be proven wrong. Some physicists argue this makes it not even science, just mathematical philosophy. But others argue we're being too harsh. String theory has revolutionized pure mathematics, leading to deep insights in algebraic geometry and topology. It's provided tools for understanding black hole entropy and has made the most precise calculations of black hole thermodynamics, matching Hawking's predictions. Juan Maldacena adds CFT correspondence, a result from string theory showing that a theory of gravity in one space can be equivalent to a quantum theory without gravity in a lower dimensional space, has become one of the most important ideas in theoretical physics. And string theory does answer the question, what is gravity made of? It says gravity is made of gravitons, which are closed-loop strings vibrating in a particular mode, propagating through a spacetime with hidden dimensions. The problem is, we might never know if this answer is right. The energy scales where string theory makes distinct predictions are Planck scale, energies quadrillions of times higher than we can probe. The extra dimensions, if they exist, are too small to see. The strings themselves are too tiny to detect. We're left with a beautiful mathematical structure that might describe reality or might be an elaborate fiction. Edward Witten, often called the smartest living physicist, has said string theory is a piece of 21st century physics that fell by chance into the 20th century. The implication, we're not smart enough yet to understand what we've discovered. We need new mathematical tools, new physical insights. Maybe in 100 years, string theory will seem obvious. Or maybe it'll be a footnote in the history of physics, a beautiful idea that turned out to be wrong. But here's the thing. Even if string theory is wrong about the details, it might be right about the big picture. It might be teaching us that asking, what is gravity made of, requires us to completely reimagine what matter and force and spacetime even mean at the fundamental level. And there's another approach to quantum gravity that takes an even more radical view. What if spacetime itself is made of something more fundamental? What if space and time aren't the bottom layer of reality? That's where we're going next, and it's going to get even weirder. While string theory says gravity is vibrations of strings in extra dimensions, loop quantum gravity takes a completely different approach. It says, forget about particles for a moment. Let's quantize spacetime itself. Let's ask what space and time are made of at the most fundamental level. And the answer loop quantum gravity gives is stunning. Space is not continuous. Space is made of discrete chunks, quantum grains of space. And these grains are connected in a network, a web of relationships, where the connections themselves are quantized. Imagine space like a fabric. From far away, it looks smooth and continuous. But zoom in far enough, and you'd see it's woven from individual threads. Loop quantum gravity says that if you could zoom into the Planck scale, you'd see that space is woven from loops quantum excitations of gravitational field lines. Carlo Rovelli, one of the founders of loop quantum gravity, describes it beautifully. Space is not a container. Space is a network of relations. What we call spacetime is the web of interactions between quantum gravitational loops. Think of it like this. Imagine the internet. The internet isn't a thing or a place. It's a network of connections between computers. Each computer is a node. Each connection is a link. The internet exists in the relationships between nodes, not in any physical substrate. Loop quantum gravity says spacetime is similar. It's not a background stage. It's an emergent structure arising from quantum relationships. In loop quantum gravity, the fundamental quantities are loop's closed curves in space, along which gravitational field lines are concentrated. These loops connect at nodes, forming a network called the spin network. Each loop carries quantum numbers representing area. Each node carries quantum numbers representing volume. Area and volume are quantized. They come in discrete chunks, multiples of the Planck area and Planck volume. This means there's a smallest possible area, about y-70 square meters. There's a smallest possible volume, about 10 to 105 cubic meters. You can't subdivide space beyond that. Space is fundamentally grainy. What if I told you this solves the black hole information paradox? When Stephen Hawking showed in 1974 that black holes emit radiation and eventually evaporate, it created a problem. Where does the information about what fell into the black hole go? In quantum mechanics, information can't be destroyed. But if a black hole evaporates completely, the information seems lost. Loop quantum gravity suggests that inside a black hole, space doesn't collapse to infinite density. Instead, quantum effects of the discrete spacetime halt the collapse. The singularity, that point of infinite density at the black hole center, doesn't actually exist. Instead, the collapsing matter bounces at the Planck scale and could potentially explode outward, forming a white hole in another region of spacetime or another universe. The information isn't lost. It's transferred. This isn't just speculation. In loop quantum gravity, physicists have done detailed calculations of black hole entropy, the measure of how much information a black hole can contain, and gotten results matching Hawking's predictions from a completely different approach. Both methods agree that black hole entropy is proportional to the surface area of the event horizon. Loop quantum gravity derives this by counting the number of possible configurations of quantum loops piercing the horizon surface. But here's the radical part. In loop quantum gravity, time doesn't exist fundamentally either. At the Planck scale, there's no flowing river of time. Instead, there are quantum events interactions between loops, and those events have causal relationships. This event influences that event. What we perceive as time is the unfolding of these causal relations. Rovelli has written extensively about this. He argues that time is an emergent, approximate concept that only makes sense for macroscopic systems like us. At the fundamental level, the universe is timeless. There's just a network of quantum events in various configurations, and we perceive a subset of those configurations as a sequence ordered in time. Think of it like watching a movie. The movie film is a stack of still frames. Each frame shows a different configuration. When you run them in sequence, you perceive motion and time. But the film itself is static. All the frames coexist. Time is the relationship between frames, not something flowing through them. Loop quantum gravity says reality might be like that film, a timeless structure that we experience as temporal because of our limited perspective. This is mind-bending, and it has profound implications. If time is emergent, then questions like, what happened before the Big Bang, might be meaningless. The Big Bang isn't an event in time. It's the boundary of time itself, the edge of the network of causal relations. Asking what came before is like asking what's north of the North Pole. In loop quantum gravity, the Big Bang might be replaced by a big bounce. The universe could have been contracting before it was expanding. At the moment when density reached the Planck scale, quantum gravitational effects would have halted the collapse and reversed it, causing the expansion we observe as the Big Bang. The universe might oscillate between expansion and contraction, bouncing eternally. So what is gravity made of in loop quantum gravity? The answer is, gravity is made of quantum relationships in the spin network. It's not made of particles flying through space. It's made of the quantum structure of space itself. The graviton, if it exists as a concept here, is an excitation of the spin network, a ripple propagating through the web of quantum loops. But here's the challenge loop quantum gravity faces. It's really good at describing quantum properties of geometry, what space is made of. But it struggles to derive Einstein's general relativity in the smooth, large-scale limit. In other words, we know that on everyday scales, Einstein's equations work perfectly. Loop quantum gravity should be able to start from its discrete quantum structure and show that when you zoom out and average over many loops, you recover Einstein's smooth curved spacetime. But proving this rigorously has been difficult. Additionally, loop quantum gravity doesn't naturally unify with the other forces. String theory at least tries to be a theory of everything. Loop quantum gravity is just about quantum gravity. You still need separate theories for electromagnetism, the strong force and the weak force. Some physicists see this as a feature maybe. Gravity is genuinely different from other forces and shouldn't be unified. Others see it as a bug, a sign that loop quantum gravity isn't the complete picture. So we have two major competing approaches. String theory says gravity is gravitons, which are vibrating strings in 10 dimensions. Loop quantum gravity says gravity is quantum excitations of a discrete spacetime network. They're both mathematically sophisticated. Both have successes and problems. Both might be partly right, or both might be wrong. And neither one has been experimentally tested. We're in the bizarre situation where our two best attempts to answer, what is gravity made of, give completely different answers, and we have no way to decide between them. But what if we're asking the wrong question? What if gravity isn't? What if I told you that gravity might not be fundamental at all? That it might be a hologram, a three-dimensional illusion, emerging from information encoded on a two-dimensional surface? And that this isn't fringe speculation, but one of the most important insights in theoretical physics from the past 30 years? Welcome to the holographic principle, and this is where physics goes full matrix on us. Here's the setup. In the 1970s, Jacob Bekenstein and Stephen Hawking proved that black holes have entropy, a measure of hidden information. But the weird part is where that entropy lives. For normal objects, entropy is proportional to volume. A box twice as big has roughly twice as much entropy because it can hold twice as many particles in twice as many configurations. But black hole entropy is proportional to surface area, not volume. A black hole's entropy equals 1/4 of its event horizon surface area measured in Planck units. This is the Bekenstein-Hawking formula, and it's been confirmed through multiple independent calculations. Think about how strange this is. All the information about everything that fell into a black hole, every particle, every quantum state is somehow encoded on the two-dimensional surface of the event horizon. It's like every 3D object you throw into a black hole gets flattened into a 2D pattern on the surface, like a hologram. In 1993, Gerard 't Hooft proposed something radical. What if this isn't just true for black holes? What if the entire universe works this way? What if all the three-dimensional physics we experience is actually encoded on a two-dimensional surface at the boundary of space? This is the holographic principle. It says that all the information in a volume of space can be described by information on the boundary of that volume. Three-dimensional reality is a hologram projected from a two-dimensional surface. But wait, you're thinking, I'm clearly three-dimensional. I have depth. I can move forward and backward, not just left, right, and up, down. Yes, you can. But the holographic principle says that everything about you, every atom, every thought, every quantum state could be equivalently described by information encoded on a distant two-dimensional surface. You're not actually on that surface. You're the three-dimensional projection of that information. Like a hologram on a credit card looks three-dimensional, even though it's encoded on a flat surface. Here's where it gets truly mind-blowing. In 1997, Juan Maldacena discovered a concrete mathematical realization of the holographic principle. He showed that a string theory with gravity in a five-dimensional anti-de Sitter space is mathematically equivalent to a four-dimensional quantum field theory without gravity on the boundary of that space. This is called the ADSCFT correspondence, and it's one of the most important discoveries in theoretical physics. It gives us a dictionary to translate between a theory with gravity and a theory without gravity. And here's the kicker. The theory without gravity is conceptually simpler and better understood. What if I told you this means gravity might be emergent? In the four-dimensional boundary theory, there's no gravity, just quantum fields interacting. But when you use the dictionary to translate into the five-dimensional bulk space, gravity appears automatically. Gravity emerges from the collective behavior of quantum fields, the way wetness emerges from many water molecules. Think of it like this. Imagine an aquarium. Fish are swimming in three-dimensional water, but you're watching from outside, and all you can see is the two-dimensional view through the glass. If you were smart enough, you could reconstruct everything about the 3D motion of the fish from the 2D patterns on the glass, their positions, velocities, interactions. The 2D surface contains all the information about the 3D interior. That's the holographic principle. Now imagine that the fish in water aren't really in the tank. They're emergent patterns arising from some more fundamental process on the glass itself. The 3D world is a useful way to describe what's happening, but it's not fundamental. The fundamental reality is the 2D surface. That's holographic emergence of gravity. This has profound implications for what gravity is made of. If gravity is emergent, if it only appears when you describe reality in certain ways, but isn't fundamental, then asking what gravity is made of is like asking what the wetness of water is made of. Wetness isn't made of anything. It's a property that emerges from many molecules. Maybe gravity is similar a collective property emerging from quantum information. Eric Verlinde at the University of Amsterdam has pushed this idea further with his theory of entropic gravity. He proposes that gravity is an entropic force. It arises from the tendency of systems to maximize entropy, like the force that causes a rubber band to contract. When you stretch a rubber band, you align its polymer molecules, decreasing entropy. The band contracts to increase entropy again. That contraction creates a force. Verlinde suggests gravity works similarly. Matter arranges itself to maximize the entropy of holographic information, and we perceive this as gravitational attraction. In Verlinde's picture, asking what gravity is made of is completely misguided. Gravity isn't made of anything. It's a statistical effect arising from information theory. There are no gravitons. There's no quantum field of gravity. There's just quantum information distributed holographically, and the laws of thermodynamics create what we perceive as gravitational force. This is controversial. Many physicists are skeptical. Verlinde's theory makes predictions about dark matter. He suggests it's not actual matter, but an emergent effect of gravity at large scales, and observations have been mixed. Some galaxy clusters seem to confirm his predictions. Others contradict them. But whether Verlinde's specific theory is right, the holographic principle itself is on solid ground. The ADSCFT correspondence has passed every mathematical test thrown at it. Thousands of papers have used it to solve problems in quantum chromodynamics, condensed matter physics, and black hole thermodynamics. It works. The philosophical implication is staggering. The three-dimensional universe we inhabit might be a kind of illusion, not in the sense that it doesn't exist, but in the sense that it's not the deepest description of reality. The fundamental description might be two-dimensional, And our 3D experience is a convenient but non-fundamental way of organizing that information. Here's what will blow your mind. If the holographic principle is right, then the number of possible quantum states in any region of space is finite and limited by the surface area bounding that region, not the volume. This means there's a limit to how much information can be packed into a volume of space. If you try to pack in more information, more particles, more quantum states, the region will collapse into a black hole, and the information will still be limited by the surface area of the resulting event horizon. This suggests that space itself has a kind of information capacity, a maximum density of reality. And this might explain why quantum mechanics and gravity are hard to unify. They're not both fundamental. Quantum mechanics is fundamental. Gravity is emergent. Trying to quantize gravity is like trying to quantize temperature or pressure. You're trying to treat an emergent, statistical property as if it were a fundamental field. But here's the problem. A DCFT correspondence works in anti-de Sitter space, which has negative curvature and different properties than our universe. Our universe appears to have positive cosmological constant. It's expanding and accelerating. We live in de Sitter space, not anti-de Sitter space. And nobody has yet found a working holographic principle for de Sitter space. We have hints and partial results, but no complete picture. So the holographic principle might explain what gravity is made of, or rather, why it isn't made of anything, but only for universes that aren't quite like ours. Whether it applies to our actual universe remains an open question. Still, it's shifted how physicists think about reality. The idea that information is more fundamental than matter, that geometry emerges from entanglement, that our 3D universe might be a holographic projection, these aren't fringe ideas anymore. They're mainstream research programs pursued at major universities and institutes worldwide. And this leads to an even deeper question. If gravity is emergent, if space-time is holographic, what is the fundamental reality from which they emerge? What is the most basic layer of existence? That question is going to take us into the strangest territory yet. Remember to hit that like button if your brain isn't completely fried yet, and subscribe because we're about to go even deeper. Drop a comment and tell me, are you still following along, or do you need me to rewind? What's the most mind-blowing thing you've learned so far? Okay, here's where we're going. What if space-time itself, the fabric of reality, is woven from quantum entanglement? What if the geometry of space, and therefore gravity, emerges from the way quantum information is entangled across the universe? This sounds like word salad, so let me break it down. Quantum entanglement is the phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance and hated it. But it's real. It's been experimentally confirmed thousands of times, and it's now the basis for quantum computing and quantum cryptography. In 2006, Shinsei Ryu and Tadashi Takayanagi made a breakthrough. They showed that in the ADS-CFT correspondence, the amount of entanglement between quantum fields in one region and another region on the boundary is directly related to the geometry of spacetime in the bulk. Specifically, entanglement entropy is proportional to the area of a minimal surface in the bulk that connects the two regions. Think of it like this. Imagine two regions on a 2D boundary. In the 3D bulk, there's a surface that connects them like a soap film stretching between two wire loops. The area of that surface tells you how much quantum entanglement exists between those two boundary regions. More area means more entanglement. But here's the revelation. The geometry of the bulk, the shape of spacetime itself, is determined by the pattern of entanglement on the boundary. Where quantum fields are highly entangled, spacetime is smooth and connected. Where entanglement is low, spacetime is disconnected or doesn't exist at all. Mark van Ramsdonk at the University of British Columbia put it starkly in a 2010 paper. Spacetime is quantum entanglement. He showed that if you gradually remove entanglement from the boundary theory, the spacetime in the bulk gradually falls apart. Full entanglement gives you smooth, connected spacetime. No entanglement gives you disconnected fragments of spacetime. The very fabric of space is woven from quantum entanglement. What if I told you this might explain why Einstein's curved spacetime works? Gravity as curved geometry could be the macroscopic manifestation of microscopic quantum entanglement. The reason objects follow geodesics through curved spacetime is because the pattern of quantum entanglement between them and the rest of the universe guides their motion. Leonard Susskind and Juan Maldacena have explored this through the A=EPR conjecture. Here's what that means. Einstein and Nathan Rosen showed in 1935 that general relativity allows for wormholes bridges through spacetime connecting distant regions. These are called Einstein-Rosen bridges, or E-A bridges. Separately, in that same year, Einstein, Boris Podolsky, and Rosen wrote about quantum entanglement, now called EPR correlations. Susskind and Maldacena proposed A=EPR. Wormholes and entanglement are the same thing viewed from different perspectives. When two particles are entangled, they're connected by a microscopic wormhole through spacetime. The geometry of the wormhole is created by the entanglement. The entanglement is sustained by the geometry. They're dual descriptions of the same phenomenon. This sounds insane, but there's mathematical evidence supporting it. For black holes, they've shown that entanglement between the Hawking radiation escaping the black hole and the interior creates wormhole-like geometric structures. The information paradox might be resolved by this. Information isn't lost when black holes evaporate because the interior and exterior remain connected via quantum entanglement, which manifests geometrically as wormholes. Think of it like this. You and your friend each have one particle from an entangled pair. In the quantum description, your particles are entangled, measuring one affects the other instantly. In the geometric description, your particles are connected by a wormhole, a geometric bridge through spacetime. These are two languages describing the same reality. If this is right, then spacetime is fundamentally relational. It doesn't exist as a background. It's generated by the relationships between quantum systems. Where things are entangled, space exists. Where they're not, space doesn't exist, or exists only weakly. This has a beautiful consequence. It might explain why space appears three-dimensional. The dimensionality of space could emerge from the structure of quantum entanglement. Different entanglement patterns might give different spatial dimensions. Our perception of three dimensions might reflect the particular way quantum information is entangled in our universe. Brian Swingle at MIT and others have worked on this, showing that certain quantum systems with specific entanglement structures naturally give rise to emergent spacetime with gravitational dynamics. You can start with a quantum system on a lattice, no spacetime. Just quantum bits entangled in particular patterns, and out pops something that behaves like curved spacetime with matter and energy. Gravity emerges automatically from the entanglement structure. Here's what will blow your mind. This suggests that the Big Bang might not be the beginning of time, but a phase transition in quantum entanglement. Before the Big Bang, quantum information might have been arranged in a pattern that didn't correspond to extended spacetime. Then, a transition occurred, maybe a quantum fluctuation, maybe something else, and the entanglement reorganized into a pattern that manifests as expanding spacetime. The Big Bang is the moment when spacetime crystallized from a more fundamental quantum structure. This also has implications for black holes. The event horizon of a black hole might be a surface of maximal entanglement between interior and exterior degrees of freedom. The information paradox arises because we're treating the black hole as if information goes behind a barrier. But if the interior and exterior are fundamentally entangled, connected by E-bridges, then information never really separates. It's distributed non-locally across the entangled system. But here's the challenge. This is all happening in the context of a DSCFT, which might not apply to our universe. And we don't yet have a complete, detailed mechanism for how entanglement patterns map to space-time geometry in realistic situations. We have toy models, simplified examples, promising mathematics. But we don't have the full theory. Still, the paradigm shift is profound. For centuries, we thought space was the stage on which physics played out. Einstein showed that the stage curves and affects the actors. Now, quantum information theory suggests the stage itself is emergent. It's built from the relationships between actors. Space doesn't contain matter. Matter and its quantum relationships create space. What is gravity made of? In this view, gravity is made of quantum entanglement specifically, the large-scale geometric manifestation of how quantum information is distributed and correlated across the universe. When you fall toward Earth, you're not being pulled by a force or following curved spacetime in some intrinsic sense. You're being guided by the pattern of quantum entanglement between all the particles in your body and all the particles in Earth, a pattern that we find convenient to describe geometrically as curved spacetime. Gravity isn't made of gravitons flying through space. It's made of the deep quantum correlations woven into the fabric of reality, correlations that create space and time themselves. And if that's true, then the question, what is gravity made of, has been pointing us in the wrong direction all along. We've been asking about the composition of the fabric when we should have been asking about the pattern of the weaving. But there's one more layer to peel back, one more revolution in our understanding. And it has to do with what happens when you look at reality, not from the perspective of stuff in space, but from the perspective of events and information flow. Let me ask you a question that's going to seem off topic at first. What is information? Is it physical? Does it have mass? Does it take up space? You might think information is abstract, just patterns, data, something represented physically, but not physical itself. But modern physics is realizing that information might be the most fundamental thing there is. More fundamental than matter. More fundamental than energy. More fundamental than spacetime. This is the information theoretic approach to physics, and it's revolutionizing how we think about gravity and everything else. Here's a key insight from thermodynamics. Information is physical. When you erase information, when you delete a bit of data, you must increase entropy somewhere else. This was proven by Rolf Landauer in 1961. The Landauer principle says that erasing one bit of information at temperature T requires dissipating at least kT lane, 2, of energy as heat. Information has physical consequences. Think of it like this. Your computer heats up when it's working hard, not just because of electrical resistance, but because computation manipulating information is a physical process that generates entropy. Information isn't an abstract concept separate from physics. It's deeply woven into the physical laws. Now, here's where it gets wild. If black holes have entropy, they contain information. When things fall into a black hole, information goes with them. But Hawking showed that black holes evaporate, seemingly destroying that information. This is the information paradox we keep mentioning. But what if the information paradox is telling us something profound? What if it's revealing that information is conserved at the deepest level, and any apparent violation, like information disappearing into black holes, must be resolved by deeper physics? Stephen Hawking eventually conceded in 2004 that information is probably conserved in black hole evaporation. The information doesn't disappear. It's encoded in subtle correlations in the Hawking radiation, but the mechanism is still debated. Is it through wormholes, A equals EPR? Through quantum corrections to black hole geometry? Through some more radical restructuring of spacetime near the horizon? The deeper point is this. Information conservation might be more fundamental than energy conservation or even the structure of spacetime. Jacob Bekenstein argued that the universe has a fundamental information capacity. Measured ultimately by the Bekenstein bound, the maximum information in a region is proportional to the area of its boundary surface, not its volume. What if I told you that this makes the universe fundamentally digital? Not digital in the sense of computers, but digital in the sense that there's a finite, countable number of possible states for any region of space. Infinity isn't physical. Physics is fundamentally discrete at the Planck scale. This connects to an idea called it from bit, coined by John Archibald Wheeler. Wheeler proposed that every particle, every field, every aspect of physical reality derives its existence from information, from yes or no questions, from bits. Reality is made of information. Think of it like this. In quantum mechanics, before you measure something, it exists in a superposition of possibilities. The measurement extracts a bit of information. You get a yes or no answer to, is the particle here? That bit of information actualizes reality. The physical world emerges from the process of answering such questions. Wheeler put it poetically. All things physical are information theoretic in origin. The universe isn't a big machine made of stuff. It's a big computer processing information. Now apply this to gravity. If space-time is emergent from quantum entanglement, and entanglement is about correlations between quantum states, i.e., information, then space-time is emergent from information. Gravity, being the dynamics of space-time, is also emergent from information. Verlaine's entropic gravity fits this picture. Gravity arises from information theory, from the tendency of systems to maximize entropy, which is a measure of information. When objects fall toward each other gravitationally, they're not following forces or curves in space. They're participating in a universe-wide optimization of information distribution. Here's the revelation. From this perspective, asking, what is gravity made of, is asking the wrong ontological question. Gravity isn't made of stuff. It's made of relationships between informational degrees of freedom. It's the way information naturally organizes itself in a universe, with quantum mechanics and thermodynamics. This might sound too abstract, but it has concrete implications. If the universe is fundamentally informational, then the laws of physics are constraints on how information can flow and be processed. The speed of light isn't just a speed limit for matter. It's a limit on how fast information can propagate. Quantum entanglement doesn't violate this, because entanglement doesn't transmit usable information. You can't use it to send messages faster than light. The holographic principle makes sense in this framework. Information is the fundamental thing, and it's limited by surface area, because that's the maximum information capacity for a region. Three-dimensional space is a convenient way to organize that information, but the information itself lives on the boundary. Gravity makes sense too. It's the emergent behavior you get when you have vast amounts of quantum information entangled in particular patterns. The curvature of spacetime is a geometric language for describing how information flows and correlates across the universe. What if I told you that you, your consciousness, your thoughts, your sense of self, are also patterns of information? Your brain is processing information. Your memories are stored information. Your decisions emerge from information processing. In a deep sense, you are an informational structure embedded in a larger informational structure we call the universe. This isn't saying you're not real or you're just data. It's saying that information is what reality is made of at the deepest level. Calling something information doesn't make it less real. It reveals what real fundamentally means. But here's the uncomfortable truth. We don't yet have a complete theory of quantum gravity based on information. We have hints, glimpses, promising starts. We have a DSCFT, which is information theoretic at its core. We have entropic gravity, which is speculative. We have Wheeler's et from bit philosophy, but we don't have equations. We can't yet write down the informational laws from which space-time and gravity emerge and then solve those equations to make testable predictions. We're like Newton before he discovered calculus. We can see the patterns, but we don't have the mathematical language to fully describe them. String theory and loop quantum gravity are attempts to write those equations in traditional terms: particles, fields, geometry. The information theoretic approach is trying something more radical: build physics from information theory first principles. But it's not there yet. So where does that leave us in understanding what gravity is made of? It tells us that the question might need rephrasing. Instead of, what is gravity made of? Which assumes gravity is a substance, maybe we should ask, what are the informational relationships that manifest as gravity? Or, what is the information theoretic structure that we perceive as gravitational interaction? And the answer, tentatively, is gravity is the large-scale manifestation of how quantum information is entangled, distributed, and processed across the universe. The geometric language of curved spacetime is one way to describe this. The particle language of gravitons is another way. The informational language of entanglement and entropy is perhaps the deepest way. But we're still figuring out the details. And that's okay. That's how science works. We're standing at the frontier, looking into the darkness, catching glimpses of something profound. We don't have all the answers, but we're asking better questions. And that brings us to something crucial. Why should you care? What does any of this abstract physics have to do with your life? That's what we're exploring next, and it's going to tie everything together in a way that makes this personal. Before we get to how this affects your life, we need to confront one more mind-bending aspect of quantum mechanics that intersects with gravity: the measurement problem. Because understanding what gravity is made of forces us to ask, what is anything made of when we're not looking at it? Here's the setup. In quantum mechanics, particles don't have definite properties until measured. Before measurement, an electron doesn't have a definite position. It's described by a wave function spread across many locations. When you measure it, the wave function collapses, and you find the electron at one specific location. But what causes the collapse? What counts as a measurement? And here's the key question: is collapse a real physical process, or just an update in our knowledge? This is the measurement problem, and it's been haunting physics for a century. And it intersects with gravity in a surprising way. In the 1950s, physicist Roger Penrose proposed that gravity might cause wave function collapse. His idea: superposition states create different configurations of space-time different gravitational fields. When the difference in spacetime curvature between superposition branches reaches a certain threshold, the superposition becomes unstable and collapses to one branch. Gravity itself causes quantum decoherence. Think of it like this. Imagine a particle in superposition, here and there simultaneously. In the here branch, spacetime curves one way around the particle's mass. In the there branch, spacetime curves slightly differently. These are two different geometric states. Penrose suggests that when the difference gets large enough, spacetime can't sustain both geometries simultaneously, and reality picks one. This is called objective collapse theory, or gravitational decoherence. It makes a testable prediction. Large enough superpositions should collapse spontaneously, even without measurement. The collapse rate depends on mass-heavier objects collapse faster. This could potentially be tested with sophisticated quantum experiments on microscopic but relatively massive objects. What if I told you that some experiments have been done, and the results are inconclusive? Some data hints at anomalous decoherence that could be gravitational. Other data is consistent with standard decoherence from environmental interactions. We're at the edge of what's experimentally possible. But here's why this matters. If gravity causes wave function collapse, then gravity is not just geometry or quantum information. It's the thing that makes quantum mechanics classical, the bridge between possibility and actuality. Gravity would be the mechanism by which the fuzzy quantum world crystallizes into definite reality. This connects to something deep, the relationship between consciousness, observation, and reality. In standard quantum mechanics, measurement, which involves a conscious observer or at least a classical measuring device, causes collapse. This leads to weird implications. Does the moon exist when nobody's looking at it? Einstein famously asked this sarcastically, but it's a real question in quantum mechanics. If gravity causes collapse, then the moon definitely exists when you're not looking, because its huge mass creates enough gravitational self-interaction to collapse its wave function constantly. Reality at large scales is definite because gravity makes it so. But here's the flip side. If spacetime is emergent from quantum entanglement, as we discussed earlier, then spacetime doesn't exist at the fundamental level, only quantum information exists. So the gravitational collapse can't be literally gravity acting on quantum states, because gravity doesn't exist at that level. It must be something else, something more fundamental that we perceive as gravitational effects. This creates a fascinating circularity. Gravity emerges from quantum mechanics at large scales, but quantum mechanics becomes classical experiences collapse due to gravitational effects. Each explains the other, but neither is fundamental. They're both emergent aspects of something deeper. The philosopher and physicist Carlo Rovelli has a different take. He argues there's no wave function collapse at all, not gravitational, not observational. Instead, quantum mechanics describes relational information. The wave function doesn't describe the particle's properties. It describes the correlation between the particle and the observer. Different observers can have different wave functions for the same particle, and that's fine because quantum states are relative, not absolute. Think of it like this. You and your friend are both looking at a box with a cat inside. Schrodinger's cat, of course. You open the box and see a live cat. From your perspective, the cat's wave function has collapsed to alive. But until your friend opens the box, or you tell her, from her perspective, the cat is still in superposition. Both perspectives are valid. Quantum states are relationships, not objective properties. This is called relational quantum mechanics, and if it's right, then asking, what is gravity made of? Is asking, what is the relationship between matter and spacetime? And the answer is, it's a relational structure. Gravity exists in the correlations between how objects and fields interact. It's not a thing in itself. This might sound like philosophical word games, but it has teeth. It resolves paradoxes. It makes predictions. And it aligns with the informational view. Reality is fundamentally about relationships, correlations, information flow. Objects don't have intrinsic properties. They have properties relative to other objects. What if I told you this means there's no absolute, observer-independent reality? There's only reality relative to a given reference frame, a given observer, a given subsystem of the universe. Your reality and an alien's reality on the other side of the galaxy might be incompatible, not because one is wrong, but because reality is perspectival. This sounds crazy, but it's where cutting-edge physics is heading. The idea that reality is objective and absolute is a classical prejudice. Quantum mechanics has been trying to tell us for a century that reality is relative and relational. We just haven't wanted to listen, and gravity fits into this. Gravity isn't an objective field existing independently. It's the relationship between mass-energy distributions and the motion of objects. From a photon's perspective, space-time looks radically different than from your perspective. Both perspectives are valid. So what is gravity made of? It's made of correlations, made of relationships, made of the structure of information as perceived from various reference frames. But this still leaves us with a practical question. If reality is relational, if gravity is emergent, if everything is information and quantum correlations, what does that mean for you? How does this change your worldview? How should you think about yourself and your place in the universe? That's where we're going next, and it's going to get personal. Okay, let's bring this home. Let's talk about what all this abstract physics means for you right now, sitting wherever you are, living your life. Here's the first big takeaway. Reality is not what it seems. The solid ground beneath you, the chair supporting you, the air around you, these are not solid, stable, independent things. They're patterns of quantum information, entangled fields, emergent structures arising from interactions at the Planck scale. The stability you perceive is statistical, not fundamental. Think of it like this. A TV screen from far away shows a smooth image. Up close, its pixels discrete, flickering, constantly changing. Reality is like that. From your macroscopic perspective, it's smooth and continuous. But zoom in to the Planck scale, and it's a seething foam of quantum fluctuations, virtual particles, information processing. Does this make reality less real? No, it makes it more interesting. The image on the screen is real, even though it's made of pixels. Your experience is real, even though it emerges from quantum processes. But here's the shift. You are not separate from this process. You're not an observer standing outside reality looking in. You're a pattern within reality, made of the same quantum information, participating in the same universal information processing. Your brain is a biological computer processing information. Your neurons are quantum systems, though they mostly behave classically due to decoherence. The thoughts you're thinking right now, the ideas forming in your mind as you watch this video, are patterns of information, propagating through neural networks, no different in principle from the patterns of quantum entanglement that create spacetime. What if I told you that consciousness itself might be an emergent phenomenon like gravity? Just as spacetime emerges from quantum entanglement, subjective experience might emerge from informational complexity in biological systems. You're not a soul piloting a meat robot. You're an informational pattern that has become self-aware, able to reflect on itself, to model its own existence. This isn't reductionist in a bad way. It's not saying you're just atoms or just information. It's revealing what you fundamentally are. A localized eddy in the information flow of the universe, a self-sustaining pattern complex enough to experience itself. And here's where gravity comes back in. Gravity is the universe-scale manifestation of information organization. You are a small-scale manifestation, but you're both doing the same thing, organizing information, creating structure, participating in the universal tendency toward complexity. The universe is not indifferent to you. It didn't create you separately. You are the universe experiencing itself, organized in one particular way. When you look at the stars, that's the universe looking at itself. When you wonder about gravity, that's the universe wondering about itself. Carl Sagan said it perfectly. We are a way for the cosmos to know itself, not poetically, but literally. The matter in your body was forged in stars. The quantum fields constituting your particles are excitations of universal fields permeating all spacetime. You are cosmically connected at the deepest level. But here's what will blow your mind. Because spacetime is emergent from entanglement, and you are entangled with everything you've ever interacted with, you are non-locally connected to vast portions of the universe. When you look at the moon, photons from the moon enter your eye and interact with your retina. That creates entanglement. You are now quantum mechanically correlated with the moon. The information that defines you extends beyond your skin. Every conversation you've had, every object you've touched, every place you've been, you've left quantum correlations. You've entangled yourself with the world. In a very real sense, you are not confined to your body. You are a distributed pattern of information extending across spacetime through entanglement relationships. Think of it like this. Drop a stone in a pond. Ripples spread outward. The ripples carry information about the stone's mass, shape, the force of impact. Are those ripples part of the stone? No, but they're information about the stone, propagating through the pond. Similarly, you create ripples in the quantum information field, through light, through gravitational effects, through every interaction, and those ripples carry information about you across the universe. When you die, your body decomposes, but the information that constitutes you doesn't disappear. Information is conserved in quantum mechanics. It disperses, it scatters into entanglement with the environment, but it remains encoded in the universe's information structure. This is the physics version of immortality. You are eternal information, not as a conscious, experiencing self that requires specific organization which ends at death, but as a pattern woven into the universe's informational tapestry. You persist forever. Does that bring comfort? Maybe, maybe not. But it's true according to our best understanding of physics. The information paradox for black holes applies to you too. Information can't be destroyed. Your unique pattern, once actualized, remains part of the universe's history forever. Now, what about free will? If you're an informational pattern emerging from quantum mechanics, do you have genuine agency? Or are you just a deterministic process playing out according to physical law? Here's where quantum mechanics gives an interesting answer. The universe is not deterministic at the quantum level. Quantum outcomes are genuinely probabilistic, not because we lack information, but fundamentally. When a quantum measurement occurs, reality branches or collapses in ways that aren't predetermined by prior states. This means your brain, processing information through neural networks that are quantum systems at base, has genuine indeterminacy built in. Your decisions aren't predetermined by the configuration of particles at the Big Bang. There's quantum randomness contributing to the process. But here's the nuance. Quantum randomness isn't the same as free will. A random number generator isn't free. It's just random. Free will would require that somehow you, the informational pattern that is your consciousness, can influence quantum probabilities, can bias outcomes based on intention, meaning, purpose. Does physics allow this? We don't know. Standard quantum mechanics says no, the probabilities are fixed by the wave function and the laws of physics. But we don't have a complete theory of consciousness. We don't know how subjective experience relates to physical process. It's possible that consciousness has some causal role we don't yet understand. What if I told you that some physicists take seriously the idea that consciousness collapses wave functions? This is the von Neumann-Wigner interpretation. Consciousness is what actualizes reality from quantum possibility. In this view, you genuinely have causal power. You collapse quantum states through observation, and that collapse is influenced by your conscious intention. This is controversial and not mainstream, but it hasn't been disproven. And if space-time itself emerges from quantum entanglement influenced by measurements and observations, then consciousness, which performs observations, might play a role in literally constructing reality. Think about that. You might not just be experiencing reality. You might be participating in creating it, moment by moment, through your observations and interactions. Not in a mystical manifesting sense, but in a physical quantum mechanical sense. But whether or not that's true, here's what definitely is true. Your choices matter. Even if they emerge deterministically or randomly from physical processes, they have real consequences. Your actions create ripples, physical, informational, causal ripples that propagate through space-time and affect others. You change the universe by existing and acting in it. And here's the empowering part. Understanding that you're an informational pattern in a universe made of information means you can intentionally shape that pattern. You can learn, grow, change. Information can be reorganized. Neural patterns can be rewired. You are not fixed. You're a dynamic process, constantly updating, constantly becoming. The same physics that describes gravity, the emergence of structure from quantum information, describes you. You are a self-organizing, complex, adaptive system. You create your own meaning, your own purpose, through the information you process and the patterns you form. Does the universe have inherent meaning? Probably not. But you create meaning through your existence. You take the raw information of sensory experience and organize it into narrative, into purpose, into value. That's what consciousness does, creates meaning from meaningless information. So what is gravity made of? Quantum information. What are you made of? Quantum information. You and gravity are made of the same stuff, just organized differently. And that makes you cosmically significant. You're not separate from the universe. You're part of its ongoing process of self-organization and self-understanding. But wait, we've been talking about gravity as if we understand it. As if the equations work and the experiments confirm everything. But here's a secret that physicists don't advertise enough. We have no idea what 95% of the universe is made of. And that's directly related to gravity. Here's the problem. When astronomers measure how galaxies rotate, they find that stars at the edges move way too fast. According to the visible matter and Newton's or Einstein's equations, those stars should fly off into space. But they don't. Something is holding them in orbit, something with mass that creates gravity but doesn't emit light. In the 1970s, Vera Rubin confirmed this effect across many galaxies. The conclusion: there must be invisible matter-dark matter providing extra gravitational pull. Estimates suggest dark matter makes up about 27% of the universe's mass energy. We see its gravitational effects, but we can't see it directly. What is dark matter? Nobody knows. The leading hypothesis is WIMPs, weakly interacting massive particles. These would be particles that have mass, so they create gravity, but don't interact electromagnetically, so they don't emit or absorb light. Despite decades of experiments trying to detect them, underground detectors, waiting for WIMPs to bump into atoms, we found nothing. Alternative ideas abound. Maybe dark matter is primordial black holes formed in the early universe. Maybe it's axions, hypothetical particles from other theories. Maybe it's something we haven't imagined yet. But here's what will blow your mind. Maybe dark matter doesn't exist at all. Maybe gravity itself works differently than we think at galaxy scales. Remember Eric Verlin's entropic gravity? He predicted that at large scales, gravity should behave as if there's extra matter, what we call dark matter, but that extra apparent mass is actually an impasse, is actually an emergent effect of entropy and information theory. Some observations fit his predictions. Others don't. The jury is still out. Modified Newtonian dynamics is another approach. Proposed by Mordechai Milgram in 1983, it says Newton's laws need tweaking at very low accelerations. Change the equation slightly, and galaxy rotation curves work without needing dark matter. But Mont struggles to explain other observations, like gravitational lensing in galaxy clusters. Then there's dark energy, an even bigger mystery. In 1998, two teams studying distant supernova discovered that the universe's expansion is accelerating. Something is pushing space apart, overcoming gravity. This something is called dark energy, and it makes up about 68% of the universe's mass energy. What is dark energy? We have no idea. The simplest explanation is the cosmological constant, a property of space itself, where every cubic meter of empty space has a tiny amount of intrinsic energy. Einstein introduced this constant in 1917 and called it his biggest blunder when he removed it. Turns out he might have been right the first time. But here's the problem. When quantum field theorists calculate how much vacuum energy empty space should have the energy of quantum fluctuations of fields in the vacuum, they get a number that's 10,120 times larger than what we observe. That's not a small discrepancy. It's the worst prediction in physics, by 120 orders of magnitude. This is called the cosmological constant problem, and nobody has solved it. Why is the observed vacuum energy so incredibly small compared to theory? Something is canceling out almost all the quantum vacuum energy, leaving just a tiny bit, but we don't know what or why. Think of it like this. Imagine calculating how much money is in your bank account. Quantum theory says you should have $10,120. You check, and you have $1. Where did the other $10,120 to $1 go? And why did exactly that amount disappear, leaving just $1? This suggests we're fundamentally misunderstanding something about quantum fields, or gravity, or vacuum, or all three. The fact that 95% of the universe is dark matter and dark energy unknown stuff means we don't really understand what gravity is acting on. What if I told you that this is the biggest crisis in physics? Not quantum gravity, not the measurement problem, the dark universe. We have equations that describe 5% of the universe. The other 95% is a mystery. And it's a mystery about gravity, because gravity is what made us notice the problem. Some physicists think dark matter and dark energy are telling us that general relativity is wrong at certain scales. Others think they're real substances we haven't detected yet. Still others think they're artifacts of our misunderstanding, maybe of quantum gravity, maybe of the holographic principle, maybe of something we haven't imagined. The James Webb Space Telescope, launched in 2021, is finding galaxies in the early universe that are more massive and structured than our models predict. Some researchers wonder if this is evidence that our cosmological model, including dark matter and dark energy, needs revision. Others say it's just pushing our models to refine their details. But here's the humbling truth. When you ask, what is gravity made of? You have to confront that we don't even know what gravity is pulling on. We see gravitational effects from things we can't detect. We see space accelerating apart for reasons we don't understand. The universe is revealing that our knowledge is fragmentary. And yet, this is exciting. This means there are enormous discoveries still to be made. The next Einstein might figure out what dark matter is, or prove it doesn't exist, and that gravity is emergent in ways we haven't grasped. The next breakthrough in physics will probably come from solving the dark universe mystery. You're alive at a time when 95% of the universe is unexplained. That's not a bug, it's a feature. It means there's so much left to discover. It means the story of physics is far from over. It means future generations will look back at our time as primitive. We didn't even know what most of the universe was made of. But it also means humility. We've spent nearly 4 hours going deep into theories of quantum gravity, string theory, loop quantum gravity, holographic principles, information theory. All brilliant ideas. All might be wrong or incomplete because we're missing something fundamental about 95% of reality. So what is gravity made of? Honestly, we don't fully know. We have pieces of the puzzle. We have beautiful mathematics. We have experiments and observations. But the complete picture eludes us. And that's okay. That's science. Science isn't about having all the answers. It's about asking better questions, building better models, testing them, revising them, and gradually approaching truth asymptotically. So after all this theory, all these brilliant ideas, string theory, loop quantum gravity, emergent gravity, holographic principles, how do we actually test any of it? How do we move from speculation to science? This is the crisis of quantum gravity. Most of the interesting phenomena happen at the Planck scale, which is absurdly beyond our experimental reach. But physicists are clever. They've found ways to look for indirect evidence, subtle effects that might leak into the observable world. Let me tell you about some of the most exciting experiments and observations happening right now. First, gravitational wave astronomy. In 2015, LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. 2 black holes, each about 30 times the sun's mass, collided 1.3 billion light-years away. The merger sent ripples through spacetime that stretched and compressed LIGO's 4-kilometer-long arms by less than 1,000th the width of a proton. Think about that precision. LIGO can detect a change smaller than an atomic nucleus across distances of kilometers. It's one of the most sensitive measurements ever made. And it works. Since 2015, LIGO and its partner detector Virgo have detected dozens of black hole mergers, neutron star mergers, and other exotic events. What does this tell us about quantum gravity? Gravitational waves travel at the speed of light, exactly as general relativity predicts. If gravity were mediated by massive gravitons, particles with mass gravitational waves would travel slower than light. They don't. This rules out many modified gravity theories. But here's what will blow your mind. Future gravitational wave detectors might be able to detect quantum features in gravitational waves. If gravitons exist, then gravitational waves are made of many individual gravitons, just as light waves are made of many photons. At some level, gravitational waves should be quantized. They should come in discrete chunks. Detecting individual gravitons is impossible, as Freen and Dyson calculated. But detecting quantum noise in gravitational waves, fluctuations from the particle nature of gravitons, might be possible with next-generation detectors like LISA, Laser Interferometer Space Antenna, planned for launch in the 2030s. LISA will have arms millions of kilometers long and will detect low-frequency gravitational waves from supermassive black hole mergers. If we can detect quantum features in gravitational waves, that would be the first direct evidence of quantum gravity. It would prove gravitons exist, or at least that gravity is quantum at some level. Second, black hole physics. Black holes are natural laboratories for quantum gravity because they're places where quantum mechanics and strong gravity meet. The event horizon of a black hole is just a few Schwarzschild radii from the center close enough that quantum effects might be detectable. The Event Horizon Telescope, which produced the first black hole image in 2019, is now looking at the black hole at our galaxy's center, Sagittarius A*. By watching matter spiral into the black hole and observing the light from just outside the event horizon, physicists hope to test general relativity in extreme conditions. If general relativity is wrong or incomplete near the horizon, if quantum corrections modify the geometry, we might see deviations from predictions. The shadow of the black hole might have unexpected features. Light paths might bend differently than predicted. So far, general relativity passes every test. But we're just beginning. Higher resolution observations, with more telescopes joining the Event Horizon Telescope network, will probe closer to the horizon. Any deviation, any anomaly, could be evidence of quantum gravity. Third, cosmological observations. The early universe, moments after the Big Bang, was a quantum system. Quantum fluctuations in the early universe got stretched by cosmic inflation and became the seeds of galaxies. When we observe the cosmic microwave background, the afterglow of the Big Bang, we're seeing the imprint of quantum mechanics on cosmological scales. If quantum gravity affects the early universe, if spacetime itself was quantized during inflation, that might leave signatures in the cosmic microwave background, specific patterns in the polarization of the microwaves, or deviations from the predicted statistical properties could indicate quantum gravitational effects. The Planck satellite mapped the cosmic microwave background in exquisite detail from 2009 to 2013. So far, everything matches the predictions of general relativity plus quantum field theory. But future missions with better sensitivity might detect anomalies. What if I told you that we might be able to test quantum gravity using tabletop experiments? It sounds crazy, but several groups are working on it. The idea: put a small but macroscopic object, maybe a tiny mirror or a microbed, into a quantum superposition. If gravity is quantum, then the superposed mass should create a superposition of gravitational fields. Place a second object nearby, and it should respond to the superposed gravity. Detecting that response would prove gravity is quantum. The challenge is isolating the experiment from decoherence. Any interaction with the environment collapses the superposition before you can measure gravitational effects. But techniques from quantum computing, extreme cold, vacuum chambers, electromagnetic traps might make it possible. In 2017, a team led by Sugata Bose at University College London proposed an experiment using two tiny diamonds, each about 1/10 of a millimeter across, cooled to near absolute zero and placed in superposition. If the diamonds interact gravitationally and become entangled, if their quantum states correlate through gravity, that would prove gravity can cause quantum entanglement, suggesting gravity itself is quantum. The experiment hasn't been done yet. It's at the edge of technical feasibility, but it could happen within a decade. If successful, it would be revolutionary. Fourth, searches for Lorentz violation. Some quantum gravity theories predict that at very high energies, spacetime becomes grainy or foam-like, and this could violate Lorentz invariance, the principle that the laws of physics are the same in all directions and for all observers moving at constant velocity. If spacetime has a discrete structure at the Planck scale, photons might travel at slightly different speeds depending on their energy. High-energy photons might move slightly faster or slower than low-energy photons because they interact differently with the spacetime pixels. This effect would be tiny, a difference of 1 part in 1020 or so. But we can test it using gamma-ray bursts, enormous explosions from distant galaxies. Different photons from the same burst, with different energies, travel billions of light years to reach us. If their speeds differ even slightly, they'll arrive at different times. By measuring arrival times precisely, we can test for energy-dependent speed. So far, no violation has been found. This rules out some quantum gravity models with large Lorentz violations. But it doesn't rule out all of them, and more sensitive observations might detect subtle effects. Finally, there's the prospect of detecting primordial gravitational waves from the Big Bang itself. During inflation, the rapid expansion of the early universe should have generated gravitational waves. These primordial gravitational waves would imprint a specific pattern called B-mode polarization on the cosmic microwave background. Detecting B-modes would confirm inflation and would tell us about the energy scale of inflation. If the energy scale is high enough, it approaches the Planck scale, meaning quantum gravitational effects were significant. That would give us indirect information about quantum gravity from the universe's first moments. Multiple experiments are searching for B-modes: BIC EP3, the South Pole Telescope, the Simons Observatory. In 2014, BIC EP2 announced a detection, but it turned out to be contaminated by galactic dust. The search continues. Detection could come any year now, or it might take decades. So we have pathways to test quantum gravity, gravitational wave astronomy, black hole observations, cosmology, tabletop experiments, Lorentz violation searches, and primordial gravitational waves. None has given us definitive evidence of quantum gravity yet, but the tools are improving. The sensitivity is increasing. The experiments are getting cleverer. Within your lifetime, we might answer the question, is gravity quantum? And if so, how? That answer will tell us what gravity is made of at the deepest level. Here's something I haven't mentioned yet that's going to tie everything together in a mind-bending way. What if the reason we can't figure out what gravity is made of is because our universe is just one of infinitely many universes, each with different gravitational properties? Welcome to the multiverse hypothesis, and it's more scientifically grounded than you might think. Let me explain how this connects to gravity. Remember the cosmological constant problem? The vacuum energy of empty space is 10,120 times smaller than quantum field theory predicts. This is bizarre, but what if it's anthropic reasoning? The anthropic principle says, we observe certain values of physical constants, not because they're special, but because those values allow observers to exist. If the cosmological constant were much larger, the universe would have expanded so fast that galaxies couldn't form. If it were much smaller or negative, the universe would have recollapsed before life could emerge. We observe a tiny cosmological constant because only universes with tiny cosmological constants have observers. But this only makes sense if there are many universes with different cosmological constants. And that's where the multiverse comes in. String theory, as I mentioned earlier, has a landscape of 10,500 possible vacuum states. Different ways the extra dimensions can curl up, each giving a different set of physical laws, different particle masses, different force strengths. What if all those possibilities are realized in different regions of a vast multiverse? What if there are 10,500 universes or more, each with different physics? In this scenario, asking, why does gravity have the strength it does, is like asking, why is Earth the distance from the Sun that it is? The answer, there are many planets at many distances. We happen to be on one where the distance allows liquid water and life. Similarly, there are many universes with different gravitational constants. We happen to be in one where the constant allows stars, planets, and life. Think of it like this. Imagine a vast multiverse as an ocean. Each bubble in the ocean is a universe. Our bubble has certain properties, 3 large space dimensions, 1 time dimension, specific values for the gravitational constant, the speed of light, the mass of the electron. Other bubbles have different properties. We exist in this particular bubble because its properties allow our existence. What if I told you that cosmic inflation, the theory that the universe underwent rapid expansion in its first fraction of a second, naturally predicts eternal inflation and a multiverse? Inflation is driven by a field called the inflaton. In most models, once inflation starts, it never completely stops everywhere. Different regions stop inflating at different times, creating bubble universes. Each bubble is causally disconnected from the other's light, from one can never reach another because the space between them is expanding faster than light. Andrei Lind and Alex Vilenkin have developed models of eternal inflation, where bubble universes constantly nucleate in the inflating space. The multiverse grows without end, spawning infinite universes with potentially different physical laws. If this is true, then asking what is gravity made of in our universe might have a different answer than what is gravity made of in another universe. Maybe in some universe, gravity is mediated by gravitons from string vibrations. In another, it's emergent from quantum loops. In yet another, it's something we haven't imagined because that universe has different dimensional structure. But here's the problem. If the multiverse hypothesis is true, it might be untestable. If other universes are causally disconnected, if no signal from them can ever reach us, how can we confirm they exist? We'd be stuck in our bubble, unable to see beyond it. Some physicists argue this makes the multiverse hypothesis unscientific. Science requires testable predictions. If a theory predicts unobservable entities, is it really science or just metaphysics? Others argue the multiverse is a prediction of our best theories, string theory and eternal inflation, so we should take it seriously even if we can't directly observe other universes. And there might be indirect tests. Collisions between bubble universes in the distant past could leave imprints on the cosmic microwave background. Some researchers have looked for these bubble collision signatures, but none have been confirmed. The multiverse also raises philosophical questions about probability and fine-tuning. If there are infinitely many universes, then anything possible, no matter how improbable, happens somewhere. Does that make our universe's properties meaningless? Or does it explain them? Think about the fine-tuning of physics. The gravitational constant, the cosmological constant, the masses of particles, many of these values seem finely tuned to allow life. Change them even slightly, and stars don't form, or chemistry doesn't work, or the universe recollapses immediately. This fine-tuning has been used as an argument for design someone set the dials just right. But the multiverse offers a naturalistic explanation. There's no fine-tuning. There are infinite universes with all possible values. Most don't have life. We observe fine-tuning because only fine-tuned universes have observers. It's selection bias. However, this opens a weird can of worms. If there are infinitely many universes, and anything possible happens somewhere, then there are infinitely many universes exactly like ours. In fact, there are infinitely many copies of you. Quantum mechanics, interpreted via the many worlds interpretation, already suggests is every quantum measurement splits reality into branches, creating parallel yous who experience different outcomes. Combined with the multiverse, this means there might be infinite versions of you across different bubble universes, and infinite versions of you in different quantum branches within each universe. Every decision you could have made, you did make in some universe. Every life path you could have taken, you are taking somewhere. Does this make your choices meaningless? Or does it make every choice infinitely significant because it determines which branch you consciously experience? I don't have an answer, but it's something to contemplate. If gravity is different in different universes, if the laws of physics vary across the multiverse, then what we've been exploring, quantum gravity, string theory, loop quantum gravity, might just be local truths about our bubble. The ultimate nature of reality might transcend our universe entirely. What if I told you that some physicists think consciousness itself might be multiversal? That your awareness might somehow span quantum branches or even bubble universes, experiencing a subjective thread through the multiverse? This is speculative, not mainstream, but it's been discussed by people like Max Tegmark at MIT in his work on the mathematical universe hypothesis. Tegmark proposes that all mathematically consistent structures exist physically as universes. Our universe is one mathematical structure among infinitely many, and conscious observers like us are mathematical patterns within those structures. We experience the universe we do because we are patterns compatible with this universe's mathematics. In this view, gravity is made of mathematics, specifically the mathematics of geometry and quantum fields. And that mathematics exists eternally in a Platonic sense, independent of physical instantiation. Physics is applied mathematics. Reality is mathematics. This is the most abstract answer to what is gravity made of that I can give you. Gravity is made of relationships within a mathematical structure that describes our universe. And that structure exists in the space of all possible mathematical structures, the ultimate multiverse. Is this right? I don't know. Neither does anyone else. But it's a framework that some serious scientists take seriously. And it highlights how far we've come from Newton's simple question about why apples fall. A. Why PIC? Why Section I? The future of gravity research. We're in the final stretch now. Let's talk about where gravity research is heading and what discoveries might be on the horizon. First, the technological frontier. The next generation of gravitational wave detectors is going to revolutionize our understanding. LIGO and Virgo have been incredible, but they detect high-frequency gravitational waves from stellar mass black holes. LISA, launching in the 2030s, will detect low-frequency waves from supermassive black hole mergers, from binary systems millions of years before they merge, and potentially from exotic sources like cosmic strings or phase transitions in the early universe. Then there's pulsar timing arrays. Pulsars are dead stars that spin and emit radio beams like cosmic lighthouses. They're incredibly regular clocks. By monitoring millisecond pulsars across the galaxy and looking for correlated timing variations, we can detect very low-frequency gravitational waves with periods of years or decades. In 2023, multiple pulsar timing arrays, ANEO-NOGRAV, EPTA, PPTA, IPTA announced evidence of a gravitational wave background, a hum of gravitational waves permeating the universe. This is likely from supermassive black hole binaries throughout cosmic history, but it could also have contributions from the early universe. If we can characterize this gravitational wave background precisely, we'll learn about the cosmic history of black holes galaxy mergers, and maybe even quantum gravity effects in the early universe. Second, the precision frontier. Atomic clocks are now so precise that they can detect gravitational time dilation over height differences of centimeters. Jun Di at GL and his team have built optical lattice clocks accurate to 1 part in 1018. These clocks can measure how time flows at different heights, testing general relativity with unprecedented precision. Future clock networks could map Earth's gravitational field in extreme detail useful for geology, hydrology, climate science. But they could also test for deviations from general relativity. If quantum corrections modify gravity at small scales, ultra-precise clocks might detect them. Third, the quantum frontier. Quantum computers are becoming powerful enough to simulate quantum field theories and might eventually simulate quantum gravity models. If we can run simulations of loop quantum gravity or simplified string theory models, we can make predictions that are currently beyond analytical calculation. Quantum sensors devices that use quantum entanglement and superposition to make ultra-sensitive measurements might detect gravitational effects impossible with classical sensors. Proposals exist for using atomic interferometers, entangled masses, or squeezed light to detect gravitons or quantum features of gravity. Fourth, the cosmological frontier. The next generation of telescopes, the Nancy Grace Roman Space Telescope, the extremely large telescope in Chile, and others will map the universe's large-scale structure in unprecedented detail. Dark matter, dark energy, and the expansion history of the universe will be constrained with percent-level precision. We'll map billions of galaxies, trace the cosmic web of matter, and test whether general relativity holds on cosmological scales. Any deviation could be evidence of modified gravity or quantum gravitational effects leaking into the large-scale structure. Fifth, the theoretical frontier. Physicists are developing new mathematical tools and new perspectives. The Amplitudes program, led by Nima Arkani-Hamd and others, is recasting quantum field theory and gravity calculations in geometric terms, finding hidden simplicities and symmetries. This might reveal new structures in quantum gravity. The holographic principle is being generalized beyond a DCFT. Researchers are trying to understand whether de Sitter space, like our universe, has a holographic description. If they succeed, it would mean we can describe our entire observable universe as quantum information on a distant horizon, a profound change in perspective. Loop quantum gravity researchers are working to derive general relativity in the classical limit and to make contact with observation. If they succeed in calculating black hole evaporation or cosmological predictions that differ from general relativity, they'll have testable hypotheses. String theorists are exploring the Swarmland program, identifying which effective field theories can arise from string theory and which can't. This constrains physics in surprising ways and might explain features like the cosmological constant. And then there are wild ideas on the fringes. What if gravity isn't fundamental, but emergent from quantum error correction codes, as some researchers have proposed? What if spacetime is a quantum error-correcting code protecting information from decoherence? What if our universe is literally a simulation running on a higher-dimensional quantum computer? These ideas sound crazy, but they're being explored mathematically at places like Caltech, Harvard, Princeton. They might lead nowhere, or they might be the seeds of the next revolution. What if I told you that the answer to "what is gravity made of" might come from a completely unexpected direction? Maybe it'll be an undergraduate who notices a pattern in data that everyone else missed. Maybe it'll be an AI that discovers a new mathematical structure. Maybe it'll be a Nobel Prize winner in 2045 whose name we don't yet know. History shows that scientific revolutions often come from unexpected places. Einstein was a patent clerk when he developed special relativity. Vera Rubin faced discrimination as a woman in astronomy, but discovered dark matter. Ed Witten came from history and linguistics before becoming the leading string theorist. The future researcher who figures out what gravity is made of might be watching this video right now. That could be you. If you're young, if you're curious, if you're fascinated by these questions, study math, study physics, think deeply, challenge assumptions. The door to fundamental discovery is still open. But even if you're not going into physics, you can appreciate the journey. You can understand that reality is stranger and more beautiful than everyday experience suggests. You can carry with you the knowledge that the ground beneath your feet is an emergent phenomenon arising from quantum information entangled across the cosmos. All right, we've been on a nearly 4-hour journey through the deepest mysteries of physics. Let's tie it all together. Let's answer, as best we can, what is gravity made of? Here's what we know for certain. Gravity is the phenomenon where mass and energy affect the motion of other mass and energy through spacetime. At everyday scales, Newton's equations describe it perfectly as an attractive force proportional to mass and inversely proportional to distance squared. At relativistic scales and in strong gravitational fields, Einstein's general relativity describes it as the curvature of spacetime. Mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. This isn't a force pulling, it's objects following geodesics through curved geometry. Gravitational waves exist and travel at the speed of light, carrying energy and momentum. They've been detected from black hole and neutron star mergers. They ripple through spacetime itself. Dark matter exists, probably, and interacts gravitationally, but not electromagnetically. We detect it through its gravitational effects on galaxies and galaxy clusters. What it's made of remains unknown. Dark energy exists, probably, and causes the universe's expansion to accelerate. It might be the cosmological constant in energy inherent to empty space, or it might be something more exotic. We don't know. Now, here's what we theorize but haven't proven. Gravity is quantum. It should have a quantum description involving discrete states, superposition, and entanglement. The quantum of gravity, if it exists as a particle, is the graviton, a massless spin-2 boson. We've never detected a graviton, and probably never will directly. Space-time might be emergent from quantum entanglement. The geometry we perceive as space might arise from patterns of quantum information and correlations. Gravity would then be the macroscopic manifestation of these microscopic quantum relationships. The universe might be holographic. All information in a volume of space might be encoded on the boundary surface of that volume. Three-dimensional reality might be a projection from two-dimensional information, and gravity might emerge in the translation between these descriptions. String theory might be right. Fundamental particles might be vibrating strings in 10 or 11 dimensions, and gravity might be one vibrational mode, the graviton. But we can't test this directly. Loop quantum gravity might be right. Spacetime might be made of discrete quantum loops forming a spin network with area and volume quantized. Gravity would be excitations of this network. But we can't test this directly either. Gravity might be emergent from something more fundamental information theory, thermodynamics, or degrees of freedom we haven't discovered. Asking what it's made of might be the wrong question if it's not fundamental. The multiverse might exist, with different universes having different gravitational properties. Our observations might be anthropically selected. We see what we see because only universes like ours allow observers. So where does that leave us? With humility and wonder. We don't have a final answer. We have pieces of a vast puzzle. Each piece is beautiful, mathematically elegant, conceptually profound, experimentally tested where possible. But we don't see how they all fit together yet. What is gravity made of? Here's my synthesis. At the deepest level we currently understand, gravity is made of relationships. It's made of correlations in quantum information. It's made of the entanglement structure that weaves reality together. It's made of the tendency of systems to maximize entropy and organize information efficiently. It's made of geometry, but geometry itself emerges from quantum relationships. In the language of particles, gravity might be made of gravitons, massless spin-2 particles that mediate the gravitational interaction, emerging from the quantization of spacetime fluctuations. In the language of geometry, gravity is made of spacetime curvature, the bending of the four-dimensional stage on which reality unfolds, determined by the distribution of energy and momentum. In the language of information, gravity is made of entanglement entropy, the holographic encoding of bulk information on boundary surfaces, the emergent dynamics arising from information theory and thermodynamics.